A proton is made of 3 quarks. That's one of the first things you learn about particle physics. 2 up quarks and 1 down quark, bound together inside every atom in your body. Simple enough. But here's what nobody tells you. If you take those 3 quarks and add up their masses, you get less than 1% of the proton's actual mass. Less than 1%. The proton weighs roughly 100 times more than the stuff it's supposedly made of. That means almost everything you weigh, almost everything that gives your body mass, doesn't come from particles at all. It comes from something else entirely. Something stranger, something more violent, something happening right now inside every atom you're made of. And tonight, we're gonna find out what that something actually is. Before we go any further, if you find this kind of deep dive into the hidden mechanics of the universe interesting, a quick like or subscribe genuinely helps the channel grow. It's a small thing, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. You're made of atoms. Everything around you is made of atoms. The chair you're sitting in, the screen you're watching, the air you're breathing, the bones in your body, the blood in your veins, all of it is atoms. And at the center of nearly every atom in the universe sits a nucleus. That nucleus is made of protons and neutrons, bound together in a tight cluster smaller than anything you could ever hope to see. These are the building blocks of the physical world. Without them, nothing solid would exist. No rocks, no water, no air, no stars, no planets, no life. Protons are everywhere. They are, in the most literal sense, the scaffolding of the visible universe. Every element on the periodic table is defined by one number, and one number alone: how many protons it has in its nucleus. Hydrogen has 1 proton, helium has 2, carbon has 6, oxygen has 8, iron has 26, gold has 79. The number of protons in an atom's nucleus determines what that element is. It determines its chemical behavior, the bonds it can form, the role it plays in the physical world. Change the number of protons, and you change the element entirely. Carbon becomes nitrogen, oxygen becomes fluorine, gold becomes mercury. The identity of every atom depends entirely on its protons. So protons matter. They matter enormously. And for a long time, physicists thought protons were the bottom of the ladder. They believed protons were fundamental, meaning they had no internal structure. They were the smallest, most basic units of matter, indivisible, irreducible, the final building blocks of reality. This was a reasonable assumption. For decades, no experiment could find anything smaller. Protons behaved as if they were point-like objects with no interior. They seemed fundamental. That turned out to be wrong. In the 1960s and 1970s, a series of groundbreaking experiments changed everything. Physicists at the Stanford Linear Accelerator Center began firing high-energy electrons at protons. The idea was simple in concept, but extraordinary in execution. If protons were truly fundamental, with no internal structure, the electrons would scatter off them smoothly, like billiard balls bouncing off a solid wall. But that's not what happened. The electrons were scattering at strange angles, ricocheting off tiny, hard objects inside the proton. Something was in there. The proton had an interior. These experiments, known as deep inelastic scattering experiments, provided some of the first direct evidence that protons were not fundamental. They were composite objects, made of smaller particles. Those smaller particles came to be called quarks. Specifically, every proton contains exactly 3 quarks. 2 of them are called up quarks, and one is called a down quark. That's the proton's recipe. 2 up quarks, 1 down quark, bound together inside a space so small it defies imagination. How small? The proton has a diameter of roughly 1.7 femtometers. A femtometer is 1 quadrillionth of a meter. If you lined up roughly 600 billion protons side by side, they would barely stretch across the width of a single millimeter. If a proton were the size of a grain of sand at that same scale would be larger than the Earth itself. The proton is extraordinarily, almost absurdly tiny. But despite being so small, the proton has mass. And mass is something physicists can measure with remarkable precision. In everyday units, the mass of a single proton is about 1.67 times 10 to the negative 27 kilograms. That number is almost meaninglessly small in terms of daily life. You would need roughly 600 billion trillion protons just to make up a single gram. A single proton weighs essentially nothing by human standards. But in the world of particle physics, the proton is not nothing. It has a specific, well-defined mass, and measuring it accurately matters enormously. Now, when particle physicists talk about mass, they don't usually use kilograms. Kilograms are fine for apples and cars and people, but they're awkward at subatomic scales. Instead, physicists use a unit called the mega-electron volt. This might sound strange because electron volts are technically units of energy, not mass. But here's where one of the most famous equations in all of science enters the picture. Einstein's equation E equals mc squared tells us that energy and mass are two sides of the same coin. They are interchangeable. A certain amount of mass corresponds to a certain amount of energy, and vice versa. Because of this deep connection, particle physicists routinely express mass in energy units. It makes the calculations cleaner and the comparisons between particles much easier. In these units, the mass of a proton is 938 mega-electron volts. That's the measured value. It's been confirmed by experiments countless times over decades. 938. Remember that number. Write it in your mind. It's going to become the center of everything we talk about tonight. Now here's where the story gets interesting. If the proton is made of 2 up quarks and 1 down quark, you would naturally expect the proton's mass to come from those quarks. That seems logical. That seems obvious. It's how mass works in every other context you've ever experienced. If you put 3 bricks on a scale, the scale reads the combined weight of those 3 bricks. If you fill a suitcase with books, the suitcase weighs as much as the books, plus the suitcase itself. The mass of a composite object is simply the sum of the masses of its parts. This is so intuitive, so deeply obvious from everyday experience, that most people never even question it. Of course, the whole weighs as much as its parts. What else could it weigh? So the proton's mass should be roughly equal to the combined masses of its 3 quarks. 2 up quarks plus 1 down quark. Add them up and you should get something in the neighborhood of 938 mega-electron volts. That's the expectation. That's what every instinct tells you should be true, but that expectation is wrong. Spectacularly, overwhelmingly, almost comically wrong. The mass of a single up quark is about 2.2 mega-electron volts. The mass of a single down quark is about 4.7 mega-electron volts. So 2 up quarks give you about 4.4 mega-electron volts. 1 down quark gives you 4.7. Add them together and you get a total of roughly 9.1 mega-electron volts. 9.1. The proton's measured mass is 938. Take a moment to let that settle in. The quarks account for less than 1% of the proton's total mass. Not 10%, not 20, not even 5, less than 1%. The three quarks that supposedly make up the proton contribute almost nothing to what the proton actually weighs. It's a discrepancy of 99%. 99% of the proton's mass has nothing to do with the masses of its quarks. That's like building a house out of materials weighing 10,000 pounds, and the finished house somehow tipping the scale at 1 million pounds. You'd stare at the house and say, something is profoundly wrong here. Where is all this extra weight coming from? There's no hidden basement. There's no secret room filled with LED bricks. The house just weighs 100 times more than the things you used to build it. That's essentially what physicists were confronting when they first compared quark masses to the proton mass. The numbers didn't add up. Not by a little, by a factor of 100. And this isn't a problem unique to the proton. The neutron has the exact same issue. A neutron is made of one up quark and two down quarks. Its mass is 939.6 mega electron volts. The quarks inside it contribute roughly the same 9 or so mega electron volts. Same enormous gap, same mystery. Every proton and every neutron in every atom in the universe has this problem. The particles they're supposedly made of account for almost none of their actual mass. What makes this mismatch even more striking is how long it took physicists to fully appreciate it. The quark model didn't arrive with a clear warning label saying that quark masses would be irrelevant. It arrived as a triumph, and the mass problem only became clear gradually, over decades of confusion and debate. When Murray Gell-Mann first proposed the quark model in 1964, and George Zweig independently proposed essentially the same idea around the same time, the goal was to explain the bewildering zoo of subatomic particles being discovered in accelerator experiments. By the early 1960s, physicists had found dozens of different particles, protons and neutrons, yes, but also pions, kaons, sigma particles, Z particles, and many more. It was chaos. Nobody understood why there were so many particles or how they related to each other. Gell-Mann's insight was that all of these particles could be understood as different combinations of a small number of more fundamental objects, which he called quarks. 3 types of quarks, later called up, down, and strange, combined in specific ways could account for every known particle. 3 quarks made a baryon, like the proton or neutron. A quark and an antiquark made a meson, like the pion. Suddenly, the chaos had order. The dozens of seemingly unrelated particles fell into neat patterns, organized by their quark content. But here is the crucial point. In the early years of the quark model, nobody knew the masses of the individual quarks. The model was about symmetry and organization, not about precise mass predictions. Physicists could use the quark model to predict which particles should exist, what their charges should be, how they should interact. And those predictions were spectacularly successful. But the question of where the masses of composite particles came from was left vague. For a while, many physicists assumed the issue would resolve itself. They assumed that once quark masses were properly measured, the mass of the proton would simply be the sum of its quark masses, perhaps with small corrections from binding energy. This was the natural expectation. It was how mass worked in every other domain of physics. Atomic masses were the sum of nuclear and electron masses minus small binding corrections. Nuclear masses were the sum of proton and neutron masses minor small binding corrections. Why should quark masses be any different? But as experimental techniques improved, through the 1970s and 1980s, a deeply unsettling picture emerged. The quarks inside the proton appeared to be light, far too light. The deep inelastic scattering experiments that confirmed quarks existed also provided information about their properties, and those properties suggested that up and down quarks were extraordinarily lightweight compared to the proton. The numbers were initially uncertain, but even the early estimates showed that quark masses were far below what would be needed to account for the proton's mass. This created a genuine crisis of understanding. Physicists had successfully explained the structure of the proton in terms of quarks, but they could not explain where the proton's mass came from. The quarks were too light. Something else had to be responsible. The quark model told you what was inside the proton, but it could not tell you why the proton weighed what it did. Some physicists initially wondered whether the quark masses were simply being measured incorrectly. Perhaps the quarks were heavier than they appeared. Perhaps the experimental techniques were flawed. But as measurements converged from multiple independent methods, the conclusion became inescapable. Up quarks really did have masses of only a few mega electron volts. Down quarks were similarly tiny. The mismatch was real, and it was enormous. Others tried to explain the mass through the binding energy between quarks, analogous to nuclear binding energy. But this explanation quickly fell apart under scrutiny. In nuclear physics, binding energy makes the nucleus slightly lighter than its individual components, not heavier. Binding energy is negative. It reduces the total mass. What was happening in the proton was the opposite. The proton was far heavier than its components. Something was adding mass, not subtracting it. And the amount being added was not a small correction. It was the entire mass, essentially. By the late 1970s, the theoretical framework of QCD was in place, and physicists began to understand qualitatively what was happening. The energy of the gluon field and the kinetic energy of confined quarks were responsible for the proton's mass. The mass came from energy, not from the intrinsic weight of quarks. But proving this quantitatively, actually calculating the proton's mass from first principles, would take another 3 decades of work and some of the most powerful computers ever built. The mystery was identified. The answer was suspected. But the proof was agonizingly out of reach. What made this period so remarkable in the history of physics is that it forced a fundamental shift in how scientists thought about mass itself. Before the quark mass problem, mass was considered an intrinsic property of particles. Things were heavy because they were made of heavy stuff. After the quark mass problem, physicists had to confront the possibility that mass was not intrinsic at all, that it could emerge from dynamics, from energy, from the behavior of a system rather than the properties of its parts. This was not just a technical revision, it was a conceptual revolution, and its implications reach far beyond particle physics, as we will see. Now think about what this means for you. Your body contains roughly 7 billion atoms. That's a 7 followed by 27 zeros. The vast majority of the mass of those atoms comes from the protons and neutrons packed into their nuclei. The electrons orbiting the nucleus are extremely light. A single electron has a mass of only about 0.51 mega electron volts, roughly 1/1800th the mass of a proton. The electrons contribute almost nothing to your total body weight. Almost all of your mass, the thing that makes you heavy, the thing that pulls you toward the ground, comes from protons and neutrons, and we've just established that almost all of the mass of those protons and neutrons does not come from the quarks inside them. So here's the implication. If you weigh 70 kilograms, less than about 700 grams of that comes from the actual intrinsic masses of the quarks in your body. Less than 1%. The other 69 plus kilograms, the overwhelming majority of your physical weight, comes from something else entirely. Something that is not matter in the way you normally think about matter. Something that is not particles in any simple sense. That is a staggering statement. Almost everything that makes you physically substantial, everything that gives your body weight and solidity and presence in the world, is not coming from the fundamental particles you're made of. It's coming from somewhere else. And figuring out where that somewhere else is requires us to look at the proton in a completely different way. Let me give you another angle on why this is so strange. In chemistry, the mass of a molecule is the sum of the masses of its atoms. Water weighs as much as 2 hydrogen atoms and 1 oxygen atom combined. Table salt weighs as much as 1 sodium atom and 1 chlorine atom. This additive principle works perfectly in chemistry because the energies involved in chemical bonding are tiny compared to the masses of atoms. The binding energy between atoms in a molecule changes the molecule's mass by less than 1/1000,000,000%. It's there, technically, but it's so small you'd never notice. In nuclear physics, the binding energy becomes a bit more significant. The mass of a helium nucleus is slightly less than the combined masses of 2 protons and 2 neutrons because energy is released when they bind together. That missing mass, that binding energy, it is what powers the sun. It's what drives nuclear fusion. But even in nuclear physics, the binding energy accounts for less than 1% of the total nuclear mass. The nucleons themselves still carry the overwhelming majority of the mass. But inside the proton, this principle doesn't just bend, it shatters. The energy involved in binding quarks together doesn't just tweak the proton's mass by a fraction of a percent, it dominates the proton's mass completely. The binding energy and the internal dynamics account for 99% of everything the proton weighs. This is not a small correction. It's the entire story. The quarks are almost irrelevant to the proton's mass. The energy is everything. You might be wondering how we can even know the masses of individual quarks if they're trapped inside protons and neutrons and can never be pulled out. That's a crucial question, and the answer reveals something deep about how modern physics works. You're right that quarks cannot be isolated. They cannot exist alone. No experiment has ever detected a free quark. And our best theories strongly suggest that no experiment ever will. Quarks are permanently imprisoned inside composite particles. Always have been, presumably always will be. So you can't simply extract a quark, set it on a subatomic scale and read off its mass the way you'd weigh a marble. Instead, physicists determine quark masses through a process of indirect measurement. They study what happens when particles collide at enormous energies in accelerators. They analyze the patterns in the collision debris, the types of particles that emerge, the energies and angles at which they fly apart. By comparing these experimental results against detailed mathematical predictions from the theory of the strong force, a theory called quantum chromodynamics, or QCD, physicists can work backward and infer the masses of the quarks. These measurements are then cross-checked against many different types of experiments and calculations to ensure consistency. The quark masses that emerge from this process are called current quark masses. They represent the intrinsic masses of the quarks themselves as fundamental particles, stripped of all the complex interactions happening around them inside the proton. And those current masses are tiny. The up quark sits at about 2.2 mega electron volts. The down quark at about 4.7. For context, there are 4 other types of quarks in nature. The strange quark, with a mass of roughly 95 mega electron volts. The charm quark, at about 1,275 mega electron volts. The bottom quark, at about 4,180 mega electron volts. And the top quark, the heavyweight champion of the quark world, at about 173,000 mega electron volts. The top quark is extraordinarily massive by particle physics standards, nearly as heavy as an entire atom of tungsten. But the up and down quarks, the 2 flavors that make up every proton and every neutron in the universe, are featherweights. They are among the lightest quarks in existence, and that's exactly what makes this mystery so sharp. The 2 most important quarks in nature, the ones responsible for building every atom of hydrogen, every molecule of water, every strand of your DNA, are almost massless. Yet the protons and neutrons they build are comparatively heavy. The gap between the masses of the parts and the mass of the whole is not subtle. It is not a minor footnote in the physics textbook. It is the dominant fact about the proton. Almost everything the proton weighs comes from something other than the quarks inside it. So where does the mass come from? This is where the story takes a turn into territory that is genuinely mind-bending. Because the answer isn't that physicists found some hidden, heavy particle lurking inside the proton. There's no 4th quark secretly adding weight. There's no mysterious dense object buried in the proton's core. The answer is far stranger and far more profound than that. The proton's missing mass comes from energy, not from particles in the traditional sense, not from some undiscovered form of matter, from energy. Specifically, from the energy of the force that holds the quarks together, and from the energy of the quarks themselves as they move and interact inside their tiny prison. Now, energy becoming mass might sound vague or abstract, but it's not. It's one of the most concrete, well-established principles in all of physics. Einstein showed that energy and mass are fundamentally equivalent. They are 2 expressions of the same underlying thing. A system that contains more energy has more mass. This is not metaphorical, it's measurable, it's physical. A compressed spring weighs slightly more than an uncompressed spring. A hot object weighs slightly more than an identical cold object. The differences are unimaginably tiny at everyday scales, completely unmeasurable with any ordinary instrument. But they're real. Energy contributes mass. Mass is a form of energy. And inside the proton, the amount of energy is staggering. There is an immense amount of energy packed into a space smaller than a trillionth of a millimeter. Energy from the force field holding the quarks together. Energy from the quarks themselves, which are not sitting still, but are careening around at velocities approaching the speed of light. Energy from virtual particles flickering in and out of existence in the quantum vacuum inside the proton. All of this energy contributes real, measurable, physical mass to the proton. The mass you feel when you step on a scale. The mass that gives your body weight and substance. The proton is not a simple, quiet, orderly structure. It's not 3 little balls sitting neatly together inside a bag. The interior of a proton is one of the most violent and dynamic environments in the entire universe. It is a storm of force and energy, raging continuously, never calming down, never reaching stillness. And that storm, that ceaseless violence packed into an impossibly small space, is where nearly all of the mass in the visible universe originates. That is where your mass comes from, not from particles, from the energy of a storm you can never see, raging inside every atom in your body right now as you listen to these words. But to understand how this works, to understand why there's so much energy inside the proton and why it behaves the way it does, we need to understand the force responsible, the force that holds the quarks together, the strongest force in the known universe, a force so powerful it makes gravity look like a suggestion, a force carried by particles unlike anything else in physics, particles that don't just carry the force but generate more of it, particles that interact with themselves in a self-reinforcing cycle of escalating intensity. We need to talk about the strong force, and we need to talk about gluons, because the gluons are the heart of this mystery. They are the reason the proton is heavy, they are the reason you are heavy, and what they do inside the proton is unlike anything else in the natural world. In everyday life, you're familiar with two fundamental forces, even if you don't think about them in scientific terms. The first is gravity. It keeps you on the ground. It holds the moon in orbit around the Earth. It keeps the Earth orbiting the sun. Gravity is the force you feel every single second of every day. The second is electromagnetism. It's the force behind electricity, magnets, light, radio waves, and the chemical bonds that hold molecules together. When you pick up a glass, the reason your hand doesn't pass right through it is electromagnetism. The atoms in your fingers repel the atoms in the glass because of electromagnetic forces between their electrons. These two forces shape your entire daily experience. Every physical sensation you've ever felt, every object you've ever touched, every light you've ever seen, it all comes down to gravity and electromagnetism. But there are two other forces in nature. Forces that operate at scales so tiny that you never encounter them directly. Forces that are hidden from everyday experience, locked away inside the nuclei of atoms, operating over distances smaller than a trillionth of a millimeter. One of them is called the weak force. It's responsible for certain types of radioactive decay. It's important, but it's not the one we care about tonight. The one we care about tonight is the strong force, the strong nuclear force, and it is, without exaggeration, the most powerful force in the known universe. How powerful? Let me give you a sense. At the scale of subatomic particles, gravity is almost unimaginably weak compared to the other forces. The electromagnetic force between two protons inside a nucleus is roughly a trillion times stronger than the gravitational force between those same protons. That's a 1 followed by 36 zeros. Gravity is essentially irrelevant inside an atom. But the strong force is roughly 100 times stronger than even the electromagnetic force, which means the strong force at nuclear distances is the most powerful interaction in nature by an overwhelming margin. If two quarks are sitting next to each other inside a proton, the strong force pulling them together is overwhelmingly, almost incomprehensibly more powerful than any other force acting on them. Gravity between those same quarks is so weak in comparison that it might as well not exist. Electromagnetism is significant, but the strong force dwarfs it entirely. The strong force is what holds quarks together inside protons and neutrons. Without it, quarks would fly apart. Protons would not exist. Neutrons would not exist. Atomic nuclei would not exist. Atoms would not exist. Chemistry would not exist. You would not exist. The strong force is the glue of reality, and that word, glue, is not accidental. Because the particles that carry the strong force are literally called gluons. They are the glue that holds the subatomic world together. Every force in nature is carried by specific particles. Electromagnetism is carried by photons. Photons are the particles of light. When two charged particles interact electromagnetically, when they attract or repel each other, they do so by exchanging photons. This might sound strange. You don't see photons flying between the electrons in a wire, or between the protons and electrons in an atom. But at the quantum level, that's exactly what's happening. The electromagnetic force is communicated through the exchange of photons, even if those photons are virtual particles that you never directly observe. The strong force works the same way in principle. It is communicated through the exchange of gluons. When quarks interact through the strong force, they do so by constantly exchanging gluons. The quarks inside a proton are perpetually throwing gluons back and forth at each other, and it is this exchange that generates the force holding them together. But here is where the similarity between photons and gluons ends, because gluons are fundamentally profoundly different from photons in ways that change everything about how the strong force behaves. And these differences are the key to understanding where the proton's mass comes from. Let me start with the most important difference. Photons do not carry electric charge. This is crucial. The electromagnetic force acts on particles that have electric charge. Electrons have charge, protons have charge, but photons, the carriers of that force, do not carry charge themselves. A photon can interact with a charged particle, but two photons cannot directly interact with each other through electromagnetism. Photons pass through each other. They don't attract or repel one another. Light beams can cross paths without affecting each other. You can shine two flashlights so their beams intersect, and the beams just pass through each other, undisturbed. This means the electromagnetic force is relatively simple. Charged particles exchange photons. Photons carry the force, but photons themselves don't generate more force. They don't interact with each other. The chain stops. The force is clean, orderly, and well-behaved. Gluons are nothing like this. The strong force acts on a property called color charge. This has absolutely nothing to do with actual color. It's just a name physicists gave to this quantum property, because it comes in 3 types, and they needed a labeling system. The 3 types are called red, green, and blue, with corresponding anti-colors. Quarks carry one of these 3 color charges, and the strong force acts on any particle that carries a color charge, just like the electromagnetic force acts on any particle that carries an electric charge. And here is the critical difference. Gluons carry color charge. The carriers of the strong force are themselves charged under the strong force. This is completely unlike electromagnetism, where photons carry no electric charge. Gluons carry the very property that the strong force acts on. This means gluons don't just transmit the strong force between quarks. Gluons interact with each other. A gluon can emit another gluon. 2 gluons can attract each other. A gluon can absorb another gluon. Gluons can even collide and produce more gluons. Think about what this means. In electromagnetism, the force carriers are passive messengers. They carry the force from one charged particle to another, but they don't generate more force themselves. In the strong force, the force carriers are active participants. They don't just carry the force, they amplify it, they multiply it, they create more of themselves. The strong force feeds on itself. This is not a minor technical detail. This is the single most important property of the strong force, and it is ultimately the reason the proton is so much heavier than its quarks. This self-interaction of gluons creates a cascade, a chain reaction of force and energy inside the proton that has no parallel anywhere else in physics. No other force in nature works this way. Gravity doesn't work this way. Electromagnetism doesn't work this way. The weak force doesn't work this way. Only the strong force, carried by gluons that interact with themselves, creates this extraordinary self-reinforcing cycle. Let me try to paint a picture of what the interior of a proton actually looks like because of this. Forget the diagrams you may have seen in textbooks. Those clean illustrations showing 3 little coloured spheres sitting peacefully inside a larger circle are not just simplified. They are fundamentally misleading. They give the impression that the proton is a quiet, static structure. 3 quarks sitting in fixed positions, held together by some invisible string. That picture is wrong. It is not even close to reality. The interior of a proton is a maelstrom. The 3 quarks, those 2 up quarks and 1 down quark, are not sitting still. They cannot sit still. The laws of quantum mechanics forbid it. A particle confined to a space as tiny as a proton must have an enormous uncertainty in its momentum. This is the Heisenberg uncertainty principle at work. The more precisely you confine a particle's position, the more uncertain its momentum becomes. And since the proton is extraordinarily small, the quarks inside it are forced into extraordinarily high states of agitation. They are moving, vibrating, oscillating, and careening around inside their tiny prison at velocities that approach the speed of light. But the quarks are not the whole story. They are not even the main story. The quarks are emitting gluons constantly, frantically. Every quark in the proton is throwing out gluons at an incredible rate. And because those gluons carry color charge, they interact with each other and with the quarks the instant they appear. A gluon emitted by one quark can be absorbed by another quark, but it can also emit another gluon before it reaches the second quark. That new gluon can emit yet another gluon, and so on. The result is a cascading explosion of gluons, each one spawning more, each one carrying color charge and interacting with everything around it. The gluon field inside the proton is not a gentle haze. It is a dense, roiling, violent storm of energy. And it's not a storm that builds up and then dies down. It rages continuously, at every moment, without pause, without fluctuation on any macroscopic timescale. The proton has been storming inside since it was created. It will keep storming until it is destroyed, if it ever is. For all we know, protons may be completely stable, existing forever, which means this internal gluon storm has no end. And that storm contains an astonishing amount of energy. Here is something most people find deeply counterintuitive. Gluons have 0 mass. A single gluon, considered as a fundamental particle, is massless, just like a photon is massless. This sounds like it should mean gluons contribute nothing to the proton's mass. If gluons weigh nothing, how can they make the proton heavy? The answer goes back to Einstein. Mass and energy are equivalent. A gluon has 0 rest mass, but it carries energy. It carries momentum. It carries color charge, and it is confined inside the proton. A massless particle that is confined, that cannot escape, that is trapped inside a system, contributes its energy to the mass of that system. This is not a loophole or an approximation. It is a fundamental consequence of E equals mc squared. If a box contains energy, that box weighs more than an empty box. It does not matter whether the energy comes from massive particles or massless ones. Energy is mass. Mass is energy. They are the same thing. And the gluon field inside the proton contains enormous amounts of energy. The gluons are constantly being created and destroyed. They're constantly interacting with each other, pulling on each other, pushing against each other, splitting and merging and branching in an unending cycle. All of this activity represents energy, and all of that energy contributes mass to the proton. But the gluon field is not the only source of this hidden energy. There is another phenomenon happening inside the proton that adds to the chaos. The gluon field is so energetic, so intense, that it spontaneously creates pairs of quarks and antiquarks out of pure energy. These are not the three quarks that make up the proton's identity. These are additional quarks, temporary ones, called virtual quark-antiquark pairs. They pop into existence from the energy of the gluon field, exist for an unimaginably brief moment, and then annihilate each other, returning their energy to the gluon field. This happens constantly, everywhere inside the proton, all the time. So the proton doesn't just contain 3 quarks and a bunch of gluons. At any given instant, the proton is a seething soup of 3 real quarks, called valence quarks, a vast and turbulent gluon field, and a constantly fluctuating population of virtual quark-antiquark pairs that pop in and out of existence faster than any clock could measure. The real quarks are outnumbered. They are outweighed energetically. They are almost lost in the noise. If you could somehow take an instantaneous snapshot of the inside of a proton, you would not see 3 quarks sitting quietly. You would see a dense, chaotic cloud of quarks, antiquarks, and gluons, all tangled together, all interacting simultaneously, all contributing energy. The 3 valence quarks would be in there somewhere, but you would struggle to pick them out from the crowd, because the virtual particles and gluons would dominate the picture. Physicists sometimes use the term partoncy to describe this interior. The word parton comes from the word part, meaning constituent. The partoncy is the collection of all the quarks, antiquarks, and gluons swarming inside the proton. When high-energy particles smash into a proton, they don't scatter off 3 neat quarks. They scatter off whatever parton they happen to hit. Sometimes it's a valence quark. Sometimes it's a virtual quark or antiquark. Sometimes it's a gluon. The proton is not 3 particles, it is a teeming population. And here is what makes this even more remarkable. When physicists carefully analyze the momentum carried by all the constituents inside the proton, they find that the gluons carry roughly half of the proton's total momentum. Half. The 3 valence quarks and the virtual quark-antiquark pairs share the other half. This was one of the most stunning discoveries of 20th century particle physics. The quarks, the particles we normally say the proton is made of, carry only about half of the proton's momentum. The other half is carried by gluons, particles that are massless and that most people have never heard of. If half the proton's momentum belongs to gluons, that means the gluon field is not some passive background holding the quarks in place. It is a dynamic, energetic entity in its own right. The gluon field is not the scaffolding, it is half the building. When you ask what a proton is made of, the answer isn't just quarks. The answer is quarks and gluons in roughly equal measure, plus a churning sea of virtual particles. The proton is as much a gluon object as it is a quark object. Now, let me try to help you visualize why the gluon field is so intense by comparing the strong force to the electromagnetic force more carefully. When two electrically charged particles move apart, the electromagnetic force between them decreases. It gets weaker with distance. This is the familiar inverse square law. Double the distance and the force drops to 1/4. Triple the distance and it drops to 1/9. Move far enough apart and the force becomes negligible. This is why atoms are electrically neutral at a distance. The positive charges of the protons and the negative charges of the electrons cancel out, and from far away, you see no net electric force. The strong force does not work this way. At very short distances, inside the proton, the strong force between quarks is actually relatively weak. This is a bizarre property called asymptotic freedom, and its discovery earned physicists David Gross, David Politzer, and Frank Wilczek the Nobel Prize in Physics in 2004. At very short distances, quarks behave almost as if they are free particles, barely interacting. This is why the deep inelastic scattering experiments at the Stanford Linear Accelerator Center worked. When the electrons probed the proton at very short distances, they saw quarks that seemed to be moving freely, bouncing around inside the proton like pinballs. But as the distance between quarks increases, the strong force does the opposite of what electromagnetism does. Instead of getting weaker, the strong force gets stronger, much stronger. As you try to pull two quarks apart, the force between them increases. The gluon field between them becomes more and more energetic. The farther apart you pull them, the more energy you pour into the field. It is as if the quarks are connected by a spring that gets stiffer the more you stretch it. Except this isn't a spring. It's a field of gluons, and it doesn't just resist stretching. It actively fights back, pouring more and more energy into the growing gap between the quarks. This behavior is unique in all of physics. No other force gets stronger with distance. Gravity gets weaker. Electromagnetism gets weaker. The weak force gets weaker. Only the strong force, because of the self-interacting nature of gluons, gets stronger when you try to separate the particles it binds. This is why the gluon field inside the proton is so extraordinarily dense and energetic. The quarks are confined to a tiny space, and the strong force is pouring enormous amounts of energy into keeping them there. Think about it like this. Imagine 3 people standing in a small room. There are elastic bands connecting each person to the other 2. Now, imagine those elastic bands are special. When the people stand close together, the bands are loose and barely noticeable. But if someone tries to walk toward the door, the bands start pulling. And the farther they walk, the harder the bands pull. Not by a little, but drastically. Each step doubles the resistance. After a few steps, the force is so enormous that no amount of effort could move them further. They are trapped. Not by walls, not by locks, but by the force itself. That's what happens inside a proton. The quarks are not trapped by a barrier. They are trapped by the nature of the force between them. The gluon field gets more and more energetic as the quarks try to separate, and it becomes impossible for them to move beyond a certain distance. They are permanently confined. And all of that energy, the enormous amount of energy stored in the gluon field as it holds the quarks in place, all of it contributes mass to the proton. The gluon field is massless in the sense that individual gluons have 0 rest mass. But the field as a whole contains so much energy that it makes the proton heavy. The energy is real. The mass is real. You can measure it. You can weigh it. It's the mass you feel when you stand on a bathroom scale. There is another way to think about the gluon field that might help cement this in your mind. In electromagnetism, the field between two charged particles contains energy. If you have a positive charge and a negative charge near each other, the electric field between them stores energy. This is real and measurable. Capacitors in electronic circuits work by storing energy in electric fields. But the amount of energy stored in electromagnetic fields is usually modest compared to the masses of the charged particles themselves. In the strong force, the energy stored in the gluon field between quarks is not modest. It is colossal. It utterly dwarfs the masses of the quarks themselves. The gluon field between and around the quarks inside a proton stores so much energy that it outweighs the quarks by a factor of roughly 100. The tail wags the dog. The field dominates the particles. The force overwhelms the things it acts on. This is what makes the proton such an extraordinary object. It is not really a collection of quarks held together by a force. It is a seething ball of force that happens to contain a few quarks. The gluons are not the servants of the quarks. In terms of energy and mass, the gluons are the dominant entity. The quarks are almost incidental. They define the proton's identity. They determine its electric charge and its quantum numbers, but they contribute almost nothing to its mass. The mass comes from the gluon field. It comes from the energy of the storm. And this is why the proton weighs so much more than its quarks. Not because there are hidden particles inside. Not because our measurements of quark masses are wrong. Not because of some exotic physics we haven't discovered yet. The proton's mass comes from the extraordinary energy of the gluon field, a field generated by force carriers that interact with themselves, creating a dense, violent, self-reinforcing maelstrom of energy inside a space smaller than a trillionth of a millimeter. Every proton in the universe contains this storm. Every neutron contains a nearly identical storm. Every atom in your body, every atom in the Earth, every atom in every star and planet and moon in the cosmos, all of them are built on this foundation of caged energy. The solid, stable, seemingly permanent matter that makes up the physical world is, at its deepest level, not solid at all. It is energy, trapped, confined, raging energy that can never escape. But we haven't finished the story yet, because the gluon field is only part of the answer. The quarks themselves are also contributing far more mass than their tiny intrinsic masses would suggest. Remember, the quarks are not sitting still. They are moving at near light speed, confined to a space so small that quantum mechanics forces them into states of extreme agitation. That motion carries enormous kinetic energy. And that kinetic energy, just like the gluon field energy, becomes mass. To understand exactly how the proton's mass breaks down, how much comes from gluons, how much comes from quark motion, and how much from other effects, we need to look more carefully at what confinement really means and what happens when you try to tear a proton apart. Because it turns out the strong force has one more trick. One more extraordinary property that makes it unlike any other force in the universe. A property that ensures the quarks can never, under any circumstances, be freed. And that property has everything to do with why the proton's mass is what it is. Inside the proton, the gluon field is extraordinarily dense and energetic. It is also clear that gluons interact with themselves, creating a self-reinforcing storm of force and energy. And it is already known that even though individual gluons are massless, the energy they carry contributes real, physical mass to the proton. But now we need to go deeper. Because the gluon field doesn't just contribute mass through its raw energy. It does something else, something that has no analog anywhere else in physics. It creates an absolute, unbreakable prison for the quarks. And the nature of that prison is itself a source of the proton's mass. This phenomenon is called confinement, and it is one of the most remarkable and in some ways most frustrating features of the strong force. Here is what confinement means in plain terms. Quarks can never be free. They cannot exist as isolated individual particles floating through space on their own. No matter how much energy you pour into a proton, no matter how violently you smash it, no matter what technique you use, you will never extract a single quark from inside it. The quarks are permanently, irrevocably trapped. They are born inside composite particles, they live inside composite particles, and if they are ever destroyed, they are destroyed inside composite particles. At no point in the process does a quark ever exist alone. This is not a technological limitation. This is not a matter of building a more powerful accelerator or a more precise instrument. This is a fundamental law of nature. The strong force simply does not allow isolated quarks. The mathematics of QCD, the theory that describes the strong force, predicts confinement, and every experiment ever performed is consistent with it. No free quark has ever been detected. Physicists have looked. They have looked in cosmic rays, in particle accelerator debris, in moon rocks, in deep ocean sediments. Free quarks do not exist. The universe appears to enforce confinement absolutely. But why? What happens when you try to pull a quark out of a proton? This is where the story becomes truly extraordinary. Let's say you have a proton and you somehow grab one of the quarks inside it. Maybe you slam another particle into the proton at enormous energy, hitting one of the quarks directly. The quark gets knocked in one direction, away from the other two quarks. You might think that with enough energy you could simply blast it free. After all, that's how things work with other forces. If you hit an electron hard enough, you can knock it free from an atom. The electromagnetic force holding the electron to the nucleus can be overcome with sufficient energy. The electron flies away, and you're left with an ionized atom and a free electron. But the strong force doesn't behave like electromagnetism. Remember what we discussed. As you pull two quarks apart, the strong force between them gets stronger, not weaker. The gluon field between the separating quarks doesn't thin out and fade. It concentrates. It narrows into a dense, energetic tube, sometimes called a flux tube or a color string. This tube of gluon field energy connects the separating quarks like an increasingly taut rubber band. And the farther apart the quarks move, the more energy is stored in this tube. You keep pulling. You keep pouring energy into the separation. The flux tube stretches. Its energy grows. The force pulling the quark back increases. You are fighting the strongest force in nature, and it is fighting back harder with every fraction of a femtometer you gain. And then, something astonishing happens. The energy stored in the flux tube reaches a threshold. There is so much energy concentrated in this stretching tube of gluon field that the energy spontaneously converts into matter. Specifically, it creates a new quark-antiquark pair, right there in the middle of the tube. A brand new quark and a brand new antiquark pop into existence out of pure energy, conjured from the field itself. And what do these new particles do? The new antiquark attaches to the original quark you were pulling away. The new quark attaches to the remaining quarks in the proton. The flux tube breaks, but instead of freeing a quark, you've created a new composite particle. Where you had one proton, you now have a proton and a meson. A meson is a particle made of one quark and one antiquark bound together. You didn't free a quark, you made a new particle. The strong force used the energy you invested in trying to separate the quarks to create entirely new quarks that immediately imprison themselves. This is like trying to break a magnet in half to isolate a north pole from a south pole. When you snap a magnet, you don't get a free north pole and a free south pole. You get two smaller magnets, each with its own north and south pole. The poles are inseparable. The act of breaking the magnet creates new poles. In the same way, the act of trying to separate quarks creates new quarks. The confinement is absolute. This process, the creation of new particles from the energy of the stretched gluon field, is called hadronization. It is observed every single day at particle accelerators around the world. When protons are smashed together at enormous energies, the quarks inside them are briefly knocked apart, but they never fly away as free quarks. Instead, within an unimaginably short time, the stretching gluon fields snap and create showers of new quarks and antiquarks. These new quarks immediately bind together, forming jets of composite particles that spray outward from the collision point. Physicists detect these jets, these cascades of newly created particles, in their detectors. They see dozens, sometimes hundreds of new particles created from the energy of the collision. But among all those particles, not a single free quark. Every quark that was created found a partner. Every quark imprisoned itself instantly, bound by the inescapable strong force. You can actually see this happen. When physicists at particle accelerators smash protons together at extreme energies, the detectors don't record individual quarks flying outward. What they record are jets, narrow sprays of dozens or even hundreds of composite particles, pions, kaons, protons, and other hadrons, all erupting from the collision point in tight cones. Each jet traces back to a single quark or gluon that was briefly knocked loose in the impact. But that quark never traveled alone. Within a distance smaller than a proton's width, the stretching gluon field behind it snapped again and again, each snap creating new quark-anti-quark pairs. Each pair immediately binding into new composite particles. The result is a cascade, a chain reaction of particle creation that converts the quark's kinetic energy into a shower of bound states. By the time the debris reaches the detector, there is no trace of a free quark. There is only the jet, a fingerprint of confinement in action. Physicists have analyzed millions of these jets. They have measured their shapes, their energies, the types of particles within them. Every single observation is consistent with confinement. The quarks try to escape. The strong force converts their escape energy into new prisons. And the jets that result are among the most direct pieces of evidence we have that quarks can never, under any circumstances, be free. The cage is absolute. The universe enforces it without exception. So let me summarize what confinement means for the proton's interior. The quarks inside the proton are trapped in a space about 1 femtometer across. They cannot leave. If they try to leave, the energy needed to separate them is converted into new quarks that prevent the escape. The system is self-correcting, self-reinforcing, and absolutely unbreakable. The quarks are prisoners of a force that responds to every escape attempt by making the walls thicker. And this confinement has a direct and enormous consequence for the proton's mass. Because of the Heisenberg uncertainty principle, The uncertainty principle is one of the most fundamental laws of quantum mechanics. It states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. This is not a limitation of measurement technology. It is a fundamental property of nature. The universe itself does not have definite values for both position and momentum at the same time. Mathematically, the uncertainty principle says that the uncertainty in a particle's position multiplied by the uncertainty in its momentum must always be at least as large as half the reduced Planck constant. The reduced Planck constant, often called h-bar, is an incredibly tiny number in everyday units, which is why you never notice this effect in daily life. The uncertainty principle is irrelevant for baseballs and cars and people. The uncertainties it requires are far too small to matter at human scales. But at the scale of a proton, the uncertainty principle becomes dominant. The quarks are confined to a region about 1 femtometer across. That is their position uncertainty. 1 femtometer. Incredibly small. And because the position uncertainty is so small, the momentum uncertainty must be correspondingly large. The uncertainty principle demands it. If you know a quark is somewhere inside a proton, and a proton is only 1 femtometer across, then the quark's momentum must be enormously uncertain. It must be fluctuating wildly. The quark must be moving fast. Very fast. How fast? The numbers work out to velocities approaching the speed of light. The quarks inside the proton are not gently drifting. They are slamming back and forth across the proton's interior at relativistic speeds. Speeds where Einstein's special relativity becomes essential. Speeds where the relationship between energy and mass becomes profoundly non-linear. At everyday speeds, the kinetic energy of a moving object is relatively small compared to its rest mass energy. A baseball flying through the air has kinetic energy, but that kinetic energy is a tiny, negligible fraction of the mass energy contained in the atoms of the baseball. You would never notice the difference in weight between a stationary baseball and a moving one. But at relativistic speeds, near the speed of light, kinetic energy becomes enormous. It grows without bound as you approach light speed. For the quarks inside the proton, moving at large fractions of the speed of light, their kinetic energy is not a small correction. It is not a rounding error. It is comparable to or even larger than their rest mass energy. The quark's motion contributes a huge amount of energy to the proton, and that energy, through E equals mc squared, becomes mass. Let me be specific about the numbers because this is important. The current best understanding from both theory and experiment breaks the proton's mass into several contributions. The total mass is 938 mega electron volts. Here is roughly how that mass is distributed. The intrinsic masses of the quarks, the bare quark masses provided by their interaction with the Higgs field, contribute about 9 mega electron volts. That is less than 1% of the total. This is the number we started with. The mass that you would expect the proton to have if the quarks were just sitting there, motionless, contributing nothing but their own weight. The kinetic energy of the quarks, their frantic motion inside the proton, contributes roughly 330 mega electron volts. That is about 35% of the proton's total mass. The quark's motion alone accounts for more than a third of everything the proton weighs. And remember, this is motion that the quarks have no choice about. They are not choosing to move fast. The uncertainty principle forces them to move fast because they are confined to such a tiny space. Confinement itself generates this kinetic energy. The act of trapping the quarks in a small space creates the motion that gives them most of their effective mass. The energy of the gluon field, the storm of self-interacting gluons that we discussed in detail, contributes roughly 330 mega electron volts as well. Another 35%. The gluon field energy and the quark kinetic energy contribute roughly equal amounts. Together, they account for about 70% of the proton's mass. The remaining roughly 30% comes from a more subtle quantum effect. The virtual quark-antiquark pairs that constantly flicker in and out of existence inside the proton, the churning sea of temporary particles being created and destroyed by the energetic gluon field, these carry energy too. Their contribution, combined with complex interactions between all the components, accounts for most of the remainder. So there it is, the full accounting of the proton's mass. Less than 1% from quark masses, about 35% from quark kinetic energy, about 35% from gluon field energy, and the rest from quantum effects involving virtual particles and field interactions. The quark's intrinsic mass is almost irrelevant. The proton's mass is overwhelmingly a product of energy of motion and energy of fields, locked inside a tiny prison by the strongest force in nature. This is mass-energy equivalence in its purest, most dramatic form. Einstein's equation E equals mc squared is often associated with nuclear weapons or with the energy output of the sun. And those are indeed consequences of mass-energy equivalence. In nuclear reactions, a small amount of mass is converted into a large amount of energy, but the proton demonstrates something even more fundamental. Inside the proton, a large amount of energy is converted into mass, not in a dramatic explosion, not in a single violent event, but continuously, permanently, as a basic feature of the proton's existence. The proton's mass is not something the proton was given at birth. It is something the proton generates from the energy of its internal dynamics every moment without interruption. Let me emphasize something crucial here because it often gets lost in simplified explanations. When physicists say the proton's mass comes from energy, they do not mean this in some vague, metaphorical, hand-waving sense. They mean it literally and precisely. The energy of the gluon field and the kinetic energy of the quarks are quantifiable, calculable amounts of energy. And those amounts of energy, when converted to mass units using E equals mc squared, give you 938 mega electron volts, the measured mass of the proton. The numbers match. This is not philosophy. It is not speculation. It is a calculable, testable prediction of quantum chromodynamics, and it has been confirmed. The importance of this cannot be overstated. Think about what the proton's mass represents in the broader context of the universe. In nearly all the visible mass in the cosmos, all the stars, all the planets, all the dust, all the gas, all the living things, nearly all of that mass is made of protons and neutrons. And we have just established that 99% of the mass of protons and neutrons comes from energy rather than from the intrinsic masses of quarks. This means that 99% of the visible mass in the entire universe is energy masquerading as matter. The stars are not heavy because they contain heavy particles. They are heavy because they contain enormous amounts of trapped energy. Your body is not heavy because the quarks inside you are heavy. You are heavy because the strong force is raging inside every atom in your body, generating energy through gluon self-interactions and quark confinement, and that energy manifests as mass. The weight you feel when you stand on a scale is not the weight of stuff. It is the weight of energy. Caged, confined, inescapable energy. This also answers a question that might have been forming in your mind. If the quarks are so light, and if most of the proton's mass comes from the energy of the gluon field and the kinetic energy of the quarks, then what gives the quarks their small intrinsic masses in the first place? After all, those 9 mega electron volts have to come from somewhere. And the answer to that question is the Higgs field. You may have heard of the Higgs boson, discovered in 2012 at the Large Hadron Collider. The Higgs boson is a particle associated with a field that permeates all of space, called the Higgs field. Certain fundamental particles interact with the Higgs field, and that interaction gives them their intrinsic mass. Quarks interact with the Higgs field. Electrons interact with the Higgs field. Other fundamental particles interact with it too. The strength of each particle's interaction with the Higgs field determines how much intrinsic mass that particle has. Particles that interact strongly with the Higgs field are heavy. Particles that interact weakly with it are light. Photons and gluons do not interact with the Higgs field at all, which is why they are massless. The Higgs field gives the up quark its 2.2 mega electron volts of mass. It gives the down quark its 4.7 mega electron volts. These are real contributions. They are not zero, but they are tiny. The Higgs mechanism, which received so much public attention when the Higgs boson was discovered, is responsible for less than 1% of the proton's mass. Less than 1% of your mass. Less than 1% of the mass of the visible universe. This is one of the great ironies of modern physics. The Higgs boson was celebrated as the origin of mass. The media called it the God particle. It was presented as the answer to why things have mass. And in one narrow technical sense, that's true. The Higgs field does give fundamental particles their intrinsic masses. Without the Higgs field, quarks and electrons would be massless, and the universe would be radically different. But the Higgs field is responsible for only a tiny sliver of the mass you actually experience. The overwhelming majority of your mass, the mass of your body, the mass of the Earth, the mass of stars and galaxies, has nothing to do with the Higgs field. It comes from the energy of the strong force. It comes from gluon fields and quark confinement, and the frantic motion of particles trapped in spaces too small for them. The Higgs mechanism is important. Without it, the quarks would be massless, and the proton would behave differently. The precise mass of the proton depends on the quark masses as inputs, even though they contribute directly only a tiny fraction. Changing the quark masses would change how the strong force plays out inside the proton, which would change the total energy, which would change the proton's mass. So the Higgs field matters, but it is not the primary source of mass in the universe. That title belongs to the strong force, to gluons, to confinement, to the energy of the proton's internal storm. Now let me draw your attention to something that makes confinement even more remarkable. We said that the strong force gets stronger as quarks move apart. This is unlike every other force in nature. But there is a subtlety here that deserves attention. At very short distances, inside the proton, the strong force is actually quite weak. Quarks that are very close together barely interact. This is the property called asymptotic freedom that we mentioned earlier. The strong force is weak at short range and strong at long range. This is the exact opposite of what you might expect, and it is the exact opposite of how electromagnetism works. This means the quarks inside the proton exist in a peculiar state. When they happen to be close together, the force between them is mild. They move relatively freely. But the instant they start to drift apart, even by a tiny fraction of a femtometer, the force begins to increase, and it increases rapidly. By the time the quarks are separated by about 1 femtometer, the full force of confinement is in effect. The quarks cannot go further. They are yanked back. Or rather, the energy in the gluon field between them reaches the point where new quarks are created, breaking the separation and restoring confinement. This interplay between asymptotic freedom at short distances and confinement at longer distances creates the specific dynamics inside the proton. The quarks move in complex, chaotic patterns. Sometimes they're close together and nearly free. Sometimes they drift apart and feel the full crushing force of the gluon field. The energy of the system fluctuates wildly at the quantum level, but the average energy, the total energy, remains constant. And that constant total energy is what gives the proton its stable, well-defined mass of 938 mega-electron volts. The proton's mass is not an arbitrary number. It is a precise consequence of the interplay between quark masses, quark confinement, quark kinetic energy, gluon field energy, and the self-interaction of gluons. Change any one of these ingredients, and the proton's mass would change. Make the strong force slightly weaker, and the gluon field would contain less energy. The proton would be lighter. Make the quark slightly heavier, and the proton would be slightly heavier too, though not by much since the quark masses contribute so little. The proton's mass is a delicate balance of many competing effects, all governed by the mathematics of QCD, and that mathematics is fiendishly complex. The self-interaction of gluons, the creation and destruction of virtual quark-anti-quark pairs, the chaotic motion of confined quarks, all of this makes the strong force extraordinarily difficult to calculate. Unlike electromagnetism, where physicists can use elegant mathematical techniques to compute answers with incredible precision, QCD at the energy scales relevant to the proton resists simple analysis. The force is too strong, the interactions are too complex. The standard tricks of theoretical physics break down. For decades, this was a serious problem. Physicists knew qualitatively that the proton's mass should come from the energy of the strong force. The basic picture was clear, but they could not calculate the proton's mass from first principles. They could not start with the equations of QCD, plug in the known quark masses and the known strength of the strong force, and derive 938 mega-electron volts as the answer. The mathematics was simply too hard. Solving that problem, proving that QCD really does predict the correct proton mass, required an entirely new approach to physics. An approach that doesn't rely on pen and paper or elegant equations. An approach that uses the raw computational power of the most advanced supercomputers on the planet. And that approach is what we need to discuss next. Because without it, everything we've said tonight would be a compelling story, but not a proven fact. The proof required machines. And what those machines found confirmed one of the most profound truths about the nature of mass and the nature of reality itself. For decades, the theory of the strong force existed in a strange and frustrating limbo. Physicists were confident that quantum chromodynamics, QCD, was the correct theory. the evidence was overwhelming. Deep inelastic scattering experiments confirmed that quarks existed inside protons. The discovery of asymptotic freedom explained why quarks behaved as nearly free particles at short distances. The patterns of particle production in accelerator experiments matched QCD predictions beautifully at high energies, where the strong force is weak enough for traditional mathematical techniques to work. But at the energy scales that matter most, the scales relevant to the proton itself, QCD was essentially unsolvable by hand. The problem was the very property that makes the strong force so interesting. At the distances relevant inside a proton, roughly 1 femtometer, the strong force is not weak. It is strong, overwhelmingly strong. And when a force is this strong, the standard mathematical tools physicists use to solve quantum field theories simply fail. Those standard tools are called perturbation theory. The idea behind perturbation theory is elegant and powerful. You start with a simple system you can solve exactly. Then you treat the force as a small correction, a perturbation, and calculate its effects step by step. Each step gives you a more accurate answer. This works brilliantly in quantum electrodynamics, the theory of the electromagnetic force, because electromagnetism is relatively weak. The corrections at each step get smaller and smaller. You can compute answers to extraordinary precision, sometimes matching experiments to 10 or 12 decimal places. Quantum electrodynamics is one of the most precisely tested theories in the history of science. But perturbation theory only works when the force is weak. When the force is strong, each successive correction is not smaller than the last. It is larger. The series of corrections doesn't converge to an answer. It diverges. It blows up. It gives you nonsense. And inside the proton, the strong force is far too strong for perturbation theory. The technique that works so magnificently for electromagnetism is completely useless for calculating the proton's mass. This meant that for years, physicists had a theory they believed was correct but could not fully verify. They could test QCD at high energies, where the force is weak and perturbation theory works, and it passed every test. But they could not calculate the most basic prediction of all. They could not start with the equations of QCD and derive the mass of the proton. They could not prove mathematically that 3 quarks bound by gluons in a confining field would produce a particle with a mass of 938 mega-electron-volts. The qualitative picture was clear. Energy from gluon fields and quark motion should account for most of the mass. But the quantitative confirmation was missing. The breakthrough came from an idea proposed by the physicist Kenneth Wilson in 1974. Wilson realized that if you could not solve QCD analytically, with equations on paper, perhaps you could solve it numerically with a computer. His idea was to replace the smooth, continuous fabric of space and time with the discrete grid, a lattice of points. Instead of calculating the behavior of quarks and gluons at every point in continuous space, you would calculate their behavior only at the grid points. This turns the impossible problem of solving QCD in continuous space into a very difficult but potentially solvable problem of crunching numbers on a lattice. This approach became known as lattice QCD, and it is one of the most computationally demanding endeavors in all of science. Here is how it works in broad terms. You set up a 4-dimensional grid, 3 dimensions of space and 1 of time. At each point on this grid, you define the quark and gluon fields. You specify the strength of the strong force. You input the known masses of the quarks, those tiny numbers we discussed, 2.2 mega electron volts for the up quark and 4.7 for the down quark. Then you let the computer simulate the behavior of these fields on the lattice. The computer calculates how the quarks and gluons interact at every grid point, how the gluon field evolves, how virtual quark-anti-quark pairs pop in and out of existence, how the quarks move within their confined space. The computer does not use perturbation theory. It does not assume the force is weak. It handles the full strength of the strong force directly, brute force. No approximations beyond the fact that space has been discretized into a grid. The finer you make the grid, the more accurately the lattice approximates continuous space, and the more precise your answer becomes. But the finer the grid, the more calculations are required, and the number of calculations grows explosively as the grid gets finer. The computational demands are staggering. A single lattice QCD calculation of the proton mass can require millions of processor hours. Not hours on your laptop. Hours on some of the most powerful supercomputers ever built. Machines filling entire rooms, consuming megawatts of electricity, running for months at a time. These are not quick calculations. They are enormous, sustained campaigns of computation, each one pushing the limits of available technology. Early lattice QCD calculations in the 1980s and 1990s were crude by modern standards. The lattices were coarse with relatively few grid points. The quark masses used were often unrealistically heavy because lighter quarks required finer grids and more computation. The results were promising but imprecise. They showed that QCD was in the right ballpark. The proton mass came out in roughly the right range. But the uncertainties were large, sometimes 20 or 30%. This was encouraging but not definitive. As computers grew more powerful, the calculations improved. In 2000, a collaboration using the CPPACS supercomputer in Japan published results with significantly improved precision. Their lattice was finer, their quark masses closer to realistic values. The proton mass they calculated was closer to the measured value, though still with notable uncertainties. The real landmark came in 2008. A European collaboration known as the Budapest-Marseille-Wuppertal Group published a calculation that, for the first time, used realistic quark masses on a lattice fine enough to give results with uncertainties of only about 2%. They start with the equations of QCD. They input the known masses of the up and down quarks and the known strength of the strong force. They ran the simulation on powerful supercomputers, and out came a proton mass of 936 mega electron volts, plus or minus about 25. The measured value is 938.3. The agreement was stunning. Starting from nothing but the fundamental theory of the strong force and the tiny masses of the quarks, the computer had produced the correct proton mass to within a few percent. The calculation confirmed, quantitatively and rigorously, that QCD accounts for the proton's mass. The gluon field energy, the quark kinetic energy, the virtual particle contributions, all of it adds up to produce exactly the mass we measure in experiments. This was not a fit. This was not an adjustment of parameters to match the data. The quark masses and the strength of the strong force were determined independently from other experiments. They were inputs, not adjustable knobs. The proton mass was a prediction, a pure output of the calculation, and it matched reality. Since 2008, lattice QCD calculations have continued to improve. More powerful computers, finer lattices, better algorithms. The uncertainties have shrunk further. Modern lattice calculations reproduce the proton mass, the neutron mass, and the masses of many other composite particles with remarkable precision. The picture is consistent and clear. The mass of the proton emerges from the energy of the strong force, and QCD describes this process correctly. But the bare summary of lattice QCD doesn't convey how extraordinary this calculation really is, or why it demands such monstrous computing power. Let me take you a step closer to what the computer is actually doing, because the method itself reveals something deep about how the proton's mass emerges. The lattice is a grid of points spread across 4 dimensions, 3 of space and 1 of time. A typical modern lattice might have something like 64 points along each spatial direction and 128 points along the time direction. That gives you roughly 34 million grid points. At every single one of those points, the computer must track the state of the gluon field. The gluon field at each point is not a single number. It is a mathematical object called a matrix, specifically a 3x3 matrix of complex numbers associated with the SU3 symmetry group of the strong force. So at each of the 34 million lattice sites, the computer is storing and manipulating matrices, and the gluon field also lives on the links between neighboring sites, not just on the sites themselves, which adds another layer of complexity. The quarks are handled differently. They exist on the lattice sites, and their behavior is described by equations that connect each site to its neighbors. Computing how quarks propagate through the lattice from one point to another requires solving enormous systems of equations. For realistic quark masses, these equations become extraordinarily difficult to solve because light quarks create long-range correlations across the lattice. The computer must account for how a quark at one point influences the field at a distant point, and this requires inverting matrices that can have millions or even billions of entries. This single operation, inverting the quark matrix, is often the most computationally expensive part of the entire calculation. But here is what makes lattice QCD truly distinctive. The computer does not solve the equations once, it solves them thousands of times. The technique uses a method called Monte Carlo sampling, borrowed from statistical physics. The idea is that the quantum behavior of the gluon field is inherently probabilistic. The gluon field fluctuates. At any given moment, the field could be in any one of an astronomically large number of possible configurations. Each configuration has a certain probability. To calculate the proton's mass, you need to average over all these possible configurations, weighted by their probabilities. Since you cannot possibly enumerate every configuration, the field has far too many degrees of freedom for that. The computer generates representative samples. It starts with some initial gluon field configuration, and then randomly adjusts it step by step, guided by the rules of QCD. Over many steps, the configurations the computer visits are distributed according to the correct probabilities. It is like randomly sampling locations on a landscape weighted by altitude. Over enough samples, you get an accurate picture of the terrain. For each sampled gluon field configuration, the computer calculates something called a correlation function. This is where the proton actually appears in the calculation. You place mathematical operators at 2 points on the lattice, separated by some distance in the time direction. One operator creates a proton-like disturbance in the field. The other operator detects it. The correlation function measures how likely it is for the disturbance to propagate from one point to the other. And here is the key insight. The rate at which this correlation function decays as you increase the time separation is directly related to the mass of the proton. A heavier particle causes the correlation to decay faster. A lighter particle causes it to decay more slowly. By measuring the decay rate across many gluon field configurations and averaging the results, the computer extracts the proton mass. This is breathtaking when you stop to think about it. Nobody tells the computer what a proton is. Nobody programs in a proton. Nobody specifies 3 quarks bound together in a ball. The computer simply simulates the quark and gluon fields on the lattice following the equations of QCD. And the proton emerges. It emerges as a pattern in the correlation functions. It emerges as a stable signal that persists across configurations. It emerges because the strong force, operating on quarks and gluons, naturally creates this bound state with a specific mass. The proton is not an input, it is an output. It appears because QCD says it must. And its mass, 938 mega electron volts, appears because the energy of the confined gluon fields and the kinetic energy of the trapped quarks add up to exactly that number. Not because anyone told the computer what number to produce, but because the physics demands it. This confirmation carries profound weight. It means we are not guessing when we say that the proton's mass comes from energy rather than from quark masses. We are not speculating. We are not relying on plausibility arguments or hand-waving analogies. We have computed it, from first principles, using the fundamental equations of the strong force, on a computer. And the answer matches the measured value. The case is closed, as firmly as anything in physics ever is. Let me now step back and ask the larger question. What does all of this mean? Not just for particle physics, but for our understanding of what matter actually is. You grew up thinking that the physical world is made of stuff. Solid, tangible, permanent stuff. Atoms are stuff. Protons are stuff. They have mass, they take up space, they make things real and solid and heavy. When you hold a rock in your hand, you feel its weight, and you think you're holding material, substance, matter. Something fundamentally different from empty space or light or energy. But the proton tells a different story. Almost everything that gives that rock its weight is not stuff in any traditional sense. It is energy. The energy of gluon fields screaming through a space smaller than a trillionth of a millimeter. The energy of quarks ricocheting at nearly the speed of light inside their tiny prison. The energy of virtual particles flickering in and out of existence in a quantum storm that never ends. That is what the rock's weight is made of. Not particles, not substance, energy. Trapped energy that cannot escape, because the strong force will not allow it. The solidity of the world is, in a very real sense, an illusion, not a complete illusion. The proton is real, its mass is real. You can measure it, weigh it, interact with it. It behaves as a stable, well-defined object with consistent properties. But its mass does not come from the thing you might intuitively think of as matter. It comes from the thing you might intuitively think of as the opposite of matter. It comes from energy. The distinction between matter and energy, which seems so obvious in everyday life, dissolves completely inside the proton. This is Einstein's equation made flesh. E equals mc squared is not just a formula for nuclear bombs. It is a description of what you are. You are energy, bound up in configurations so stable that they behave as solid matter. Every atom in your body is a tiny engine of confined energy, held together by the strongest force in nature, manifesting as mass through the most fundamental equation in physics. Consider what this means for the visible universe as a whole. Stars, planets, moons, asteroids, comets, dust, gas, everything you can see through a telescope, all of it is made primarily of protons and neutrons. And the mass of all those protons and neutrons is 99% energy. The entire visible universe, every galaxy, every star, every world, is overwhelmingly made not of stuff, but of energy in disguise. When an astronomer measures the mass of a star, what they are really measuring is the total energy content of the strong force fields inside the star's atoms. When a geologist estimates the mass of the Earth, they are estimating the total confined energy of the gluon fields in every proton and neutron in the planet. The sun burns through nuclear fusion, converting hydrogen into helium and releasing energy. But the energy it releases is only a tiny fraction of the energy already stored in the protons and neutrons of its fuel. The mass difference between hydrogen and helium nuclei, the mass that gets converted to sunlight, is less than 1% of the total mass involved. The other 99%, the energy that keeps each proton and neutron massive, remains locked away, untouched, unreleased. The strong force holds it too tightly. In principle, if you could somehow disassemble protons and neutrons completely, converting all their mass back into free energy, the energy released would be roughly 100 times greater than what nuclear fusion provides. This is not practically achievable. The strong force makes it essentially impossible to fully disassemble a proton, but it illustrates just how much energy is locked inside ordinary matter. Every kilogram of any substance contains within its protons and neutrons an amount of energy that dwarfs any energy source humans have ever used. Let me address something that often causes confusion. People sometimes hear that mass comes from energy and conclude that mass is not real. That matter is somehow fake, or that the physical world is an illusion. This is a misunderstanding. The energy inside the proton is real, it is measurable, it interacts with gravity, it has inertia, it does everything that mass is supposed to do, because it is mass. Mass and energy are not different things pretending to be each other. They are the same thing, experienced in different ways depending on context. The energy of the gluon field is mass. The kinetic energy of confined quarks is mass. They are not approximations of mass or substitutes for mass. They are mass in the fullest and most complete sense of the word. What has changed is our understanding of what mass is at a fundamental level. Mass is not an intrinsic property of most particles. It is not built into the fabric of quarks in any significant way. Mass is a property of systems. It emerges from the interactions and dynamics within those systems. The proton has mass not because its parts are heavy, but because its internal dynamics contain enormous energy. Mass is emergent. It arises from complexity, from confinement, from the interplay of forces and particles inside a system. This is a deep and subtle point. In physics, we distinguish between fundamental properties and emergent properties. A fundamental property is something that exists at the most basic level of reality. An emergent property is something that arises from the behavior of many simpler components working together. Temperature, for example, is an emergent property. A single atom does not have a temperature. Temperature only makes sense when you have a large collection of atoms and can describe their average motion. Similarly, the proton's mass is emergent. A single quark has a tiny mass. A single gluon has no mass. But when you combine quarks and gluons in a confined system governed by the strong force, mass emerges. 938 mega electron volts of it. This realization changes how we think about the Higgs field and the origin of mass. The Higgs field is real and important. It gives fundamental particles their intrinsic masses. Without the Higgs field, electrons would be massless and would travel at the speed of light. Chemistry would be impossible. Atoms as we know them could not form. The universe would be a radically different place. The Higgs field is essential for the structure of reality. But the Higgs field is not responsible for most of the mass in the universe. It accounts for the tiny intrinsic masses of quarks and electrons. The rest, the vast majority, comes from the strong force. This means there are two distinct mechanisms of mass in the universe. One is the Higgs mechanism, which gives fundamental particles their bare masses. The other is the strong force mechanism, which generates mass through confinement and dynamic energy. The second mechanism is overwhelmingly dominant. It accounts for 99% of the mass of visible matter. The Higgs mechanism accounts for less than 1%. If the Higgs field had never existed, if quarks were truly massless, the proton would still have mass. Not exactly the same mass, because the quark masses do influence the dynamics slightly, but the proton would still be heavy. Calculations suggest that in a hypothetical universe with massless quarks, the proton mass would be only a few percent different from what it is in our universe. The strong force would still confine quarks, gluons would still self-interact, the internal storm would still rage, energy would still manifest as mass, the proton would still exist, and it would still be heavy. The Higgs field contributes less than 1% of the proton's mass directly, and even its indirect effects on the proton mass are modest. This is a remarkable conclusion. It means the mass of the visible universe is mostly independent of the Higgs mechanism. Turn off the Higgs field, and you would destroy chemistry. You would eliminate atoms as we know them, but you would not eliminate mass. The protons and neutrons would still be massive. The strong force would still do its work. Mass, in the broader sense, would survive the loss of the Higgs field. It is the strong force, not the Higgs, that is the true architect of mass in our universe. So let me bring this all the way home. You are sitting somewhere right now, listening to these words. Your body has mass. You can feel it. You feel the pull of gravity holding you to the surface of the earth. You feel the weight of your limbs. You feel the solidity of the chair beneath you, or the ground beneath your feet. All of that sensation, all of that physical reality comes from the protons and neutrons inside your atoms. And almost all of the mass of those protons and neutrons comes from energy. From gluon fields and quark motion and virtual particle creation, all of it governed by the strong force, all of it raging inside spaces so small you could never see them with any instrument, all of it happening right now, at this very moment, inside every single atom in your body. Your mass is not what you think it is. You are not heavy because you are made of heavy building blocks. You are heavy because you are made of energy that cannot escape. Trillions upon trillions of tiny storms, each one raging inside a single proton, each one generating mass through the sheer intensity of confined energy. The weight you carry is the weight of imprisoned light, of force fields locked in an eternal struggle, of quarks screaming through cages too small to ever break free of. This is true not just for you. It is true for everything. Every rock, every drop of water, every breath of air, every star in the sky. The mass of the visible universe, the thing that bends space and time, the thing that creates gravity and holds galaxies together, almost all of it is the energy of the strong force, locked inside protons and neutrons, manifesting as the solid, tangible, weighty reality we experience every day. And the truly extraordinary thing is that this works. The proton is stable, it does not fly apart, the energy does not leak out, the storm does not subside. As far as we can measure, the proton is either perfectly stable or has a lifetime so long that it exceeds the current age of the universe by at least 20 orders of magnitude. The proton was stable when the first atoms formed a few 100,000 years after the Big Bang. It was stable when the first stars ignited. It was stable when the Earth formed 4.5 billion years ago. It is stable now, and it will almost certainly be stable long after our sun has died and our solar system has scattered into the void. The proton is one of the most durable objects in the known universe, and its durability comes from the same source as its mass: the strong force, the confinement of quarks, the self-reinforcing gluon field that gets stronger when you try to disrupt it. The proton endures because the force that creates its mass also prevents its destruction. The cage that traps the energy also protects it. The prison is also a fortress. You began tonight perhaps thinking that the proton was simple. 3 quarks bound together. A basic building block. Something that weighs what it weighs because of the particles inside it. But the proton is not simple. It is one of the most complex, dynamic, and extraordinary objects in all of physics. Its mass is a product of the most powerful force in nature, operating through mechanisms that defy everyday intuition. Its interior is a seething ocean of gluons and virtual particles, more violent than the core of any star, more energetic per unit volume than any other environment in the known universe, and it is everywhere, inside every atom, inside you, inside the Earth, inside every star and every planet circling every star, in every galaxy in the observable cosmos. The proton's hidden storm is the foundation of the physical world. The mass it generates is the mass you feel, the mass you live with, the mass that makes reality solid and tangible and real. The next time you hold something heavy, a book, a stone, a glass of water, remember what you are actually holding. You are not holding matter in the way you once imagined. You are holding trapped energy. You are holding the accumulated fury of countless gluon fields, the kinetic energy of quarks moving at nearly the speed of light, the ceaseless creation and annihilation of virtual particles. All of it bound together by a force so powerful that nothing in the universe can break it. All of it manifesting as the simple, familiar sensation of weight in your hand. That is what the proton really is. That is where your mass really comes from. Not from stuff. From storms. Not from substance. From energy. Not from the particles themselves, but from the extraordinary, violent, beautiful physics happening inside them. You are made of trapped light. You always have been. And there is something extraordinary about the fact that you know this now. For almost all of human history, nobody knew. Ancient philosophers debated what matter was made of. Some thought it was earth, water, air, and fire. Some thought it was indivisible atoms. Some thought it was a continuous substance that could be divided forever. They argued about it for centuries, for millennia, without resolution, because they had no way to look inside matter and see what was actually there. Even after modern science began, even after atoms were discovered and their structure was mapped, the deepest truth remained hidden. Physicists in the early 20th century knew about protons and electrons. They could weigh them, count them, and track their behavior. But they had no idea that the proton's mass was a product of energy rather than substance. They assumed the proton was fundamental, indivisible, a solid little marble of matter. They had no reason to suspect that its interior was a roiling ocean of force fields and virtual particles. It took the combined efforts of thousands of physicists working over the better part of a century to unravel this truth. Experimentalists building enormous accelerators, smashing particles together at higher and higher energies, piecing together clues from the debris. Theorists were developing the mathematical framework of quantum chromodynamics, wrestling with equations that resisted every conventional technique. Computer scientists are designing algorithms and building machines powerful enough to simulate the strong force on a lattice. All of these people, across decades, across continents, contributed to the picture you now have. The picture of a proton whose mass comes from energy, not stuff. You are the beneficiary of one of the greatest intellectual achievements in the history of the human species. The understanding that mass, the most basic, most tangible, most seemingly obvious property of the physical world, is not what it appears. That the weight you feel in your bones, the solidity of the ground beneath your feet, the heft of every object you have ever lifted, all of it is energy. Energy that was trapped inside protons within a millionth of a second of the Big Bang and has remained trapped ever since. Energy that has persisted through the formation of the first atoms, the ignition of the first stars, the birth of galaxies, the formation of planets, the emergence of life, and the evolution of conscious minds capable of asking where mass comes from. That energy is still there, inside you, right now. Every proton in every atom in your body carries the same storm it has carried since the universe was less than a second old. The gluon fields are still raging, the quarks are still confined, the virtual particles are still flickering in and out of existence. Nothing has changed inside those as protons since they formed. They are among the oldest surviving structures in the cosmos. And they are inside you right now, making you real, making you heavy, making you solid, making you here. The universe created matter from energy in its first moments, and that matter has endured for 13.8 billion years, stable and unchanging, because the strong force will not let the energy escape. You're not just observing this process from the outside, you are made of it. Every breath you take, every thought you form, every sensation you feel is built on the foundation of trapped energy inside protons that have existed since the beginning of time. So, the next time someone asks you what you're made of, you'll know the answer most people never learn. You are not made of particles, not in the way you once imagined. You are made of the energy of the strongest force in the universe, locked inside the smallest structures in nature, manifesting as the solid, tangible, undeniable reality of your own existence. And that is perhaps the most beautiful thing physics has ever revealed, that the world is not what seems, that the solid is made of the formless, that weight comes from weightless things, that you are at the deepest level a symphony of forces pretending to be still.